of the distributed load. Okay, we can find the equation of this distributed load. Then, so we're going to find what is omega as a function of x. Okay, then after that we're going to substitute. Okay, we're going to substitute into dv over dx is equal to minus omega as a function of x. Okay, then after this we're going to integrate the first time, right? We integrate the first time, so we will have v as a function of x. Okay, so when we integrate, we get minus omega as a function of x dx plus by c1, right? And then we know that v as a function of x is equal to dm by dx. Okay. Now, why over here we all of a sudden have a cx? Okay, because we don't have what? If you look at our limits, we don't have any limits at all. When you don't have limits, okay, to find c1 without limits, okay, so I'm going to write on the side without limits. Right, to find c1, okay, to find c1, right, we need to have what? We need to have boundary what condition, right? We just talk about boundary condition. You only can identify your C1s or your constants if you know your what boundary condition. But over here we don't have limits. That's where we need to use our boundary condition. Okay, so from here we have v as a function of x. Then this is equal to dm by dx. Then the next one you integrate again. Okay, you integrate the second time, so you have m as a function of x. Okay, you integrate twice, minus omega x dx1 dx twice. Now you have plus c1x plus by what? C2. Okay, what you realize is we bypass the necessity to find the what? We don't need the what? We bypass this technique, as I mentioned before. We bypass the need to find the distance of where the equivalent load is acting on. Okay, we just need to integrate. That is the power of this technique. Okay, now, so we're going to find, okay, so from here, we're going to find the equation of the distributed load. Okay, we will find this equation of the system. So we're going to find this equation. So we're going to draw the equation of the distributed load first. Okay, so this is your omega, and then you have a line across. This is your x. Okay, so we have 0 over here. This is your 6,000, 12,000, 18,000, right? And then this is your distance, which is equal to 6. And then you have your load distribution looking like this. Okay, so this is a load distribution diagram. So the first thing we're going to do first is we are going to find the function of the line. For our stage is pretty straightforward. Okay, so we know that over here is a linear function, right? So omega as a function of x is equal to the gradient. So the gradient is delta y. So this is 12,000 divided by delta x divided by 6 multiplied by the x plus by the y-intercept. Okay, so where I get 12,000 from is this distance. so from sorry, I was not looking at my diagram at all. It's here. Okay, so this distance from here to here, this is your delta y, and this is your 12,000, and this is your delta x is equal to 6. Okay, so that is where we get our, so this is your delta x. Okay, so gradient is delta y over delta x, and it's positive, right? Positive slope. So I put down here positive slope. So from here, and the 6,000 over here, this is your y-intercept. And over here, I'll write this down. This is your gradient. Okay, so now we have omega as a function of x. So this will be equal to 2,000. 12,000 divided by 6 will be 2,000 x plus by 6,000. Okay, so now we have this already. Okay, so the next thing we're going to substitute. Okay, so we're going to use dv, right? We're going to use dv by dx is equal to minus omega as a function of x. All right, and we know what is omega as a function of x, so I'm going to call this equation that I've written earlier equation number 1. Okay, so this will be it. So our omega x is equation number 1, so it's minus 2,000 x minus by what? 6,000. Okay, then we do v as a function of x, so we integrate, right? So when we integrate, is equal to minus 2,000 x squared divided by 2 minus by 6,000 x plus by c1, right? Plus by c1, and this is also equal to dm by dx. Okay, so this is our equation number 2. Now, knowing our equation number 2, right? Now we are going to go back to our boundary condition. Okay, so now you see the screen with the boundary condition, right? So we are going to use this boundary condition that I'm going to highlight. So I'm going to highlight when x is equal to 0, v is equal to what? 0. Okay, so we're going to use this boundary condition. So we go to the other slide now. Okay, so we're going to substitute when x is equal to 0, v is also 0 into equation number 2. So what we get is, therefore, right, everything is equal to 0, therefore c1 is equal to 0. Okay, so when that's the case, you get v as a function of x is equal to minus 1,000 x squared, right, minus by 6,000 x, and this whole thing is equal to dm by dx. And because this equation is evolved from equation 2, we call it equation 2a. Okay, then from here we integrate again. Okay, we integrate again, so m as a function of x is equal to minus 1,000 x cubed over 3 minus by 6,000 x squared over 2 plus by c2. This is our equation number 3. Okay, so we get our equation number 3, and then from our equation number 3, right, we're going to look at our boundary condition again. Okay, we're going to look at a boundary condition. So we're going to look at boundary condition. So I'm going to highlight the boundary condition in blue. So when x is equal to 0 now, m is also equal to what? M is equal to 0 also. So we're going to use that boundary condition. Okay, So we're going to use that boundary condition that we've just written. So we're going to substitute x is equal to 0, moment is also equal to 0 into equation number 3. Right? So therefore, we just found out that C2, oops, sorry, you guys cannot see now, my bad. So we just found out that C2, I'll bring this further up so you can see. Is equal to 0. Okay, so from here, we know our moment equation is equal to minus 1000 x cubed minus by 3000 x squared. Okay, so that is our solution. Okay, so this is equation 3a. So next we're going to plot. Okay, we will plot our shear force and bending moment equation. Okay, so now we can plot the distribution of the shear force and bending moment. Okay, so we're going to plot this out. So by looking at our equation, everything will be negative. Okay, so this is our x, and our y-axis I'm going to represent two axis. Okay, so it can be v or it can be m. Okay, so this is just a sketch. So let's say if this is our 6 meter. So if we now going to do, okay, if we going to find the magnitude now, okay, so v as a function of x, we know that this is equal to minus 1000 x squared minus by 6000 x. So when x is equal to 6, this will be equal to 6 times 1000 plus by 6000. So it's minus 72,000. Okay, Newton. And then m as a function of x. Okay, so the function. So let's do v as a function of x first. Okay, so 72,000. So is a set phase, right? It's just x squared. So the function will look like this. Okay. So this represents our v as a function of x. Okay. So I'll use. Okay, v as a. So our moment equation, we have what? Moment equation is minus 1000. Okay, minus by. Okay, so m, distance 6 meters. So 6 power 3 times 1000 divided by 3. Then plus by 3000 times by 36 is equal to 180. Okay, 180,000 minus. So minus 180. Okay, so it'll be somewhere around here. And then it'll be a set phase. I miss it. So it'll be a set phase. Right? So this over here, this represents this function over here. Okay, like what I told you guys before, right? If we go back to our boundary condition, okay, so like what I told you before, if we go back to our boundary condition, right, we state this, okay, that I'm going to highlight them in yellow now. Then when x is equal to 6, we're going to have maximum what? Shearing force, and we're going to have the maximum bending moment. Okay, so likewise, when you see over here, when you